Hi. In this lesson on 6.4, I want to teach you about enzymes and what they do in chemical reactions. So, if you recall, a chemical reaction is just a rearrangement of the bonds between atoms that can result in a change in the amount of energy that they have as potential chemical energy. And in this section, I want to show you how we can talk about the energy in reactions, and then specifically about how enzymes modify energy associated with reactions. And then after that, I want to tell you a little bit about how enzymes actually function in a physical way rather than in terms of energy. And then finally, about how their effectiveness depends on conditions. So let's start with that first one and how to talk about energy in chemical reactions. All right. Um, so, oh, blah. Um, Chemical reactions often change the amount of energy that is stored in the chemicals, which is to say that reactants sometimes have more energy than the products after a reaction, or sometimes they have less. We call the amount of energy that can be transferred to or from a reaction the free energy of that reaction. And that the amount of difference between reactants and products with regard to their energy is called the delta G. So G stands for Gibbs, which is a guy who invented the concept of free energy as a convenient way of talking about the energy actually available in chemicals to do work. So we call it G for Gibbs, and the reason there's a delta there is because it's a reference to a difference, the amount of change in free energy between products in a reaction and the reactants that made them. Now, a catalyst in a reaction is a material that accompanies a chemical reaction and that makes the reaction more likely to happen. But unlike the reactants, they are unchanged by the reaction and remain so even once the products are made. Here's an example of how we would note a chemical reaction, both with some symbols showing the shapes of the molecules and also their chemical formulas. So on the left side of this equation, it's not an equation, it's actually a reaction. What you see is sucrose, a molecule you've been working with in lab. And sucrose is a molecule with lots of carbons. It's a disaccharide, which is to say that it has two connected monomers of monosaccharides, and they were connected by a dehydration synthesis reaction. And you can break those apart by adding a water molecule in a classic hydrolysis reaction. And if you do that, it splits into two, both monomers of sucrose. The glucose is one of them and fructose is the other. If you look at those two, they are, in fact, the same chemical formula, but they are not the same chemical structure. They're actually mirror images of one another. And the reaction is made more likely by the enzyme sucrase. So you would write the name of the enzyme above the arrow that denotes the course of the reaction. On the left, you write the products. Sorry, on the left, you write the reactants, and on the right, you write the products. Okay. So that's sort of standard notation for a chemical reaction. And if you want to talk about the energy of the reaction, then we in a standard way, use this kind of graph. Let me see if I can move my camera. No, I can't move my camera. And yet it is too big. There we go. What you're looking at here is a graph of, on the x-axis, a kind of an estimate of time. sort of the before time and the after time of a chemical reaction. And before, what you have are reactants, and after, what you have are products. And in between is sort of the series of events that occur in the transition from reactants to products. This reaction begins with reactants that have higher level of energy than products. And what happens between the before and after of the reaction is a loss of energy from the system. So we say that delta G is negative, and whenever the reactants have more energy than the products, or if we say delta G is negative, then we also say that it's a spontaneous reaction. So this is a spontaneous reaction. And it's symbolized by a rearrangement of bonds between these four units. Here A and B are connected as one compound, C and D are connected as another compound. And here it's the same four units, but the bonds are rearranged, which is what happens in a chemical reaction. And now A and C are connected, B and D are connected. Spontaneous reactions would result in you turning into mush if there weren't some kind of barrier to those reactions happening spontaneously in your body. And there is an energy barrier that prevents spontaneous reactions from occurring, and we call that barrier the activation energy. It's energy that has to be put into a reaction, even if the reaction is spontaneous, in order for that reaction to occur. And the symbol for the activation energy is capital E with a little a subscript, or capital A subscript. And what that activation energy does is it creates conditions in which the transition from reactants to products is highly likely. And once you reach that transition state, then it spontaneously results in product. So here's the same graph with the reactants and products shown over the course of the progress of the reaction, with a negative delta G, which is to say that reactants have more energy than products, a spontaneous reaction with some activation energy. And the graph I just showed you was the one illustrated with this black curve. If reactions happen spontaneously without activation energy, they can't happen at all with activation energy because it's a barrier. It prevents the reactions from happening. And so the way your body controls when and where reactions happen is by controlling when and where the barrier is lowered for activation energy. And by lowering that barrier, the probability of the reaction happening is much greater, and it occurs. So there are compounds that can lower those barriers, and those compounds are, as a class, known as catalysts. So a catalyst is some kind of compound or material that can lower the activation energy of a reaction. In nature, you find lots of different catalysts. Metals are common catalysts. Even mud can be a catalyst. But in living systems, we use proteins as catalysts. And when a protein serves as a catalyst for reactions, it gets the name enzyme. So enzymes can lower the activation energy of chemical reactions in your body. And what you're looking at here is what that looks like in terms of free energy. So in the absence of the enzyme, the activation energy is very high. And with the enzyme, it has been lowered so that the reaction is more probable. Now, I do want to make a nuanced point here, and that is that the activation energy is the only thing the enzyme can change. The enzyme cannot lower the energy of the reaction and actually influence this region between the reactants and the products. These energy states are features of the reactants and products themselves, and they are not altered by a catalyst. Okay, the next thing I want to say about oh my goodness, sorry about this. The next thing I want to say about enzymes is that the way that they lower activation energy, we're on part 2 here, is by binding to the reactants. And when we talk about reactants in the context of enzymes, then we use a synonym for reactants, which is substrate. So I'm going to say substrate instead of reactant because I'm talking about reactants in the context of enzymes. And in this section, I'm going to tell you about how enzymes bind to substrate and how they lower activation energy. I'm also going to explain that enzymes' ability to function is sensitive to environmental conditions, which you can vary, and thus vary the function of the enzymes. All right, so here we go. Here is a physical model of not a physical model, it's a computer model that is meant to look physical, of an enzyme. It's, as you can see, a long tangled chain of little amino acids, all drawn in blue here. And it has a unique shape. And what you see here is a reactant. In this case, I think it is carbonic acid. And it fits in very well into this little space that the enzyme has in it. This space is called the active site because this is where the close association occurs between the enzyme and the substrate. And in fact, when the substrate binds in the active site, it forms a complex that can even be more tightly associated when they're together. So you can see that the little active site closed over that little molecule, the substrate for the reaction. It's worth noting that this fit is a very good fit that is unique, which is to say that this enzyme will be capable of catalyzing exactly one chemical reaction. It can't bind to any other substrate, nor can it cause that substrate to become any other products than the products you'll see of this reaction. So for every chemical reaction in your body, there's a unique enzyme that can catalyze it. They are very specific, which is different from catalysts that you find outside of living systems, metals, muds. Those can often catalyze multiple different kinds of reactions. Okay, so we're going to look at the same enzyme, but this time in more cartoon style, and then in a series of events that is a cycle. So here it is again, that little enzyme. This enzyme is working with those earlier models we saw earlier. Earlier models we saw earlier. Speak English. There we go. It's dealing with these models. So the AB and CD reactants turning into the AC and BD reactants. All right, so we're leaving our carbonic acid model. Here we go. Here's the AB reactant and the CD reactant. And together they are the substrate that will bind to the enzyme to form this enzyme substrate complex. And in this cartoon, you can see the very particular shapes of these molecules fit very perfectly to the active site of this enzyme that holds onto it tightly. There, they convert to products. Notice the shapes of the outlines haven't changed, but the arrangement of connections between the two, what were reactants and are now products, are there. This isn't always true. Sometimes the whole product changes shape altogether, and then it no longer fits in the enzyme. The point is, once products are made, they fall away from the enzyme. The enzyme is released and can be reused, which is to say that as long as there's enzyme present that is not occupied doing reactions, it can be reused over and over. So as long as enzyme is around and there is substrate around, the reaction will occur in living systems. Okay. What happens in that active site depends on the enzyme, but there are several things that can happen that make it more probable that the reactants turn into products. One is that the the enzyme puts tension on the chemical bonds of the reactants, essentially putting them in that transition state. Another is that it can create chemical conditions inside that active site, like changes, sort of local changes in pH, that drive it to a transition state. Or it can even transiently bond to one or both of the reactants so that they are in a conformation that is more likely to rearrange the bonds again to form the products. So there are lots of things that can happen inside that active site, and each enzyme has sort of a different combination of how it works. There isn't one way that they work. So here's the thing: cells can control when and where chemical reactions occur in their body by controlling when and where they produce these enzymes. And they can control that by responding to environmental signals that tell them to make enzymes. The example I use for ninth graders is that when they turned 12, they got signals from the environment that they had reached a critical age. And at that point, that triggered the onset of the assembly of all sorts of steroid hormones through a series of chemical reactions that were driven or catalyzed by enzymes. And those hormones drove them into that very uncomfortable transition to adulthood that we call puberty. All right. So I think the last thing I want to say about enzymes is that their effectiveness can vary. And so they're enzymes are, because they are proteins themselves, they are susceptible to damage. And the things that can damage enzymes are the things that can damage any large organic molecule, such as heat or acidity or any other number of stresses. And what you see here are some interesting enzymes that illustrate how that works. So what you're looking at here, let's just look at this one black curve here at the top. This is the optimal temperature right here at 37 degrees Celsius for a typical enzyme in a person. It is not coincidental that its optimal functionality is exactly the same temperature as the average body temperature of a human. Natural selection has favored that optimality. But what we know is that as temperatures get colder, the ability of the enzyme to catalyze the reaction declines, and that's simply because everything goes slower as temperatures go down because molecules don't move as fast. But on the reflexive side of that curve, it's not the same. It's not a mirror image because temperature actually denatures proteins, and so there's a much more rapid and sudden decline in the functionality of enzymes above that temperature. So that by the time we're just a few degrees above the optimal body temperature, enzymes stop working at all. Incidentally, this is why a low fever is not bad for you, but a high fever is bad for you. High fevers can actually really damage the proteins in your body. So you should avoid very high fevers if you can. A low fever is not bad. Okay. What's interesting is that over here you're looking at a similar shaped curve, but its optimum is a fundamentally different temperature. This is an enzyme that is in a particular kind of bacterium that lives in very, very hot environments, such as the hot springs and geysers of Yellowstone National Park. This particular one happens to love 75 degrees C, which is hot. It's very hot, and its optimum is at 75 degrees. But the shape of these diminishing effectiveness is just the same as for these over here. In other words, the rates of reactions are highest around the optimum. They gradually decline in a sort of S-shaped curve away as you get colder, but it's a much more abrupt decline as you get hotter for the same reasons. It is not just temperature that affects the performance of enzymes. Other things like, pH can too. And if we look at this bottom set of curves, that's illustrated here. These are the functionality of two enzymes that are both found in humans, one in the stomach and one in the intestines. Now, the stomach is a very acidic place, whereas the intestines are slightly basic. Remember, 7 is neutral and 8 is just barely more acidic, more neutral, more basic than neutral, whereas the stomach is very, very acidic due to the hydrochloric acid that's in there. And they are optimized. These enzymes are optimized for their local environments. Notice, however, that the damage that pH does is equivalent on either side of the curve. So this doesn't have an uneven shape like the ones up here. They're more mirror imaged curves. And here, just for your joy, is an example of one of the hot geysers that you find at Yellowstone National Park. I hope you guys see it someday because it is very impressive and beautiful. Okay, I'll stop there for 6.4 and put 6.5 in a separate little video. All right.